Right. So by why that is important? Okay, why that is important? Okay, this is because now if we look at our critical stress, so we have I, right? We have I at the numerator, and we have a at the denominator. Yes, right? So we're going to let R squared is equal to I over A. Right? R squared is equal to I over A. Right? So we change, then therefore our critical stress is equal to pi squared E, right? R squared over L squared A. Or I can rewrite this equation as in equal to pi squared E divided by A. Why do I have A? The A will disappear, sorry. Right? So this is equal to L squared over R squared. Okay. Then you will see a lot of times textbooks do this, okay? L over R squared. So now to take note is this, L over R is also known as the slenderness slenderness ratio. Okay. So I'm going to call this, after writing so long, this is probably our equation number 9. So equation number 9 is only valid with centric axial loading condition. Okay, it's only. So centric loading means if you have a structure like this, right? And if this is your centroid, right? Your load is applying on the centroid. Okay. If you have a structure, same structure, not really the same, but let's say a structure like this, and this is your centroid where buckling will occur. This is where your centroid where buckling will occur. And your applied load is applied at a distance T and a certain distance X down here. Okay, this is not centric loading. Okay, this is not centric loading. Okay. So it is only applicable on the left, the structure on the left hand side, but not on the right hand side. Okay, now, how will this help you? Okay, so we have this equation 9 over here. Okay, we have this equation 9. How will this help us by using equation 9? So we're going to put in some values. Okay, so what does it actually mean? Okay, so we are going to apply equation number 9. Okay, we're going to apply equation number 9. So we are going to have stress allowable is equal to 250 times 10 to the power 6 Pascal. Okay, and our Young's modulus is equal to 200 times 10 to the power 9 Pascal. Okay. So this put us to, we know the formula, stress critical is equal to what? I can't remember. My short-term memory is equal, pi squared E over L over R squared. Okay. So we know the allowable is a critical, so this is equal to 250 times 10 to the power 6 is equal to pi squared E, which is 200 times 10 to the power 9 over L over R squared. So we're going to determine our L over R is equal to square root of pi squared multiplied by 200 times 10 to the power 9 divided by 250 times 10 to the power 6. So our L over R ratio is equal to 88.85 or 88.86. Okay. So what does this mean? Okay, we have a number L over R 88.86. What does it actually mean? So physically, now I'm going to sketch a graph now. Okay. So on our x-axis is our L over R ratio. Okay. So we start from 0, 20, 40, 60, 80, 100, 120, 140, 160. So this is our L over R ratio. Then we have our y-axis. Okay. Our y-axis is our stress allowable. Okay. So I'm going to highlight a line over here. This is where our 250 times 10 to the power 6 comes in. Okay, that's our stress, right? Then on our x-axis, I'm going to highlight a line, and this line, so this is 88. Yeah. So at this point, this is 88.86. Okay. So physically, what does it mean? Okay. From 0 to 88.86, the allowable load is what? 450. Right? After that, the structure, the allowable load, the structure is able to carry will decrease. Okay. Now, why is that? Okay. If your L over R structure is in the region of the right-hand side, okay, buckling becomes the dominant I can't spell dominant now, okay, becomes the failure mode. Okay, the right-hand side becomes the failure mode. What does it mean? It means that you have to consider what? Buckling. You cannot just look at the allowable stress. Okay. If it's less than 8.86, your design criteria is different. Okay. If it's so when it's less than 8.86, right? You can use stress allowable is equal to P over A, or you can use deflection is equal to PL over AE. Why PL over AE? Because all this is still under what? Axial loading consideration. So you can ignore, right? So sometimes when you do analysis, right? You know the length of your beam, right? You know the cross-sectional you're going to use. You know the type of radius of gyration you can get, right? Then you calculate. Then after you calculate, your L over A ratio is 8.86. Okay. So if your L over R ratio, let's say your length that you use will generate a smaller value over here, like 40, then you can ignore what? The length, right? So remember, R, okay, so how does this work? Okay, so I'll give you an example. Okay, so let's say we want to use a certain beam. Okay, we want to use this beam over. Let me copy and paste. Bear with me. I do apologize for a sec. Okay, so now you have decided, right? You have decided to use this structure over here. Okay, for example, you decide to use a structure over here. Okay, you like this, right? Then you look at this as 356. Okay, so you have your R is equal to 0.356. Right? So you also can, so we know that the material you use is have a allowable stress of 250 and Young's modulus of 200, right? So we know that your L over R is equal to 88.86. And then your length, right? 88.86 multiplied by 0.356, right? So 88.86. Right? So it's 31.63 meters. So what does this mean? If the structure that you design, if the length, this length over here, if the length, right, is less than 31.63 meters, okay, do not consider buckling analysis. Bulking. Come on, Eugene, buckling analysis. Not necessary. However, if your length is greater than 31.63 meters, must consider buckling or failure by buckling. Okay. So that's how you trigger buckling analysis or ignore buckling analysis. Okay. Now, when buckling will occur, right, also have condition. Okay. I repeat again, when buckling occur, when buckling occur has condition. What do I mean by condition? Okay. So now the next thing that we are going to go for, right, is an extension of Euler's formula. It's not difficult. These are easy stuff. This is seriously. This is so much easier than shearing stress. Okay, initially the math like holy elastic curve. Okay, it's nothing. Okay, because once I go into application, this is so easy to do. Okay, let's look at the extension. Okay, let's look at the extension of Euler's formula. Okay, let's look at Euler's formula. So the extension of Euler's formula is based on how the structure is held. Okay, how the structure is held, right? So let's look at when I say how the structure is held, is it both ends are pinned? Is it one end free, one end is pinned, or is it built in and pinned, so on and so forth? And there's a logic behind it, okay? There's a logic behind. So condition number one, right? Condition number one. So I'll get pictures. I have pictures of this, which I have not posted. My bad. Okay. Condition number one. Okay. So condition number one, what you see is one end is fixed